then we shall discuss about the Euler's equation. Euler's equations deal with the equation of motion for ideal flow. Ideal fluid means when mu or viscosity of the fluid is assumed to be 0. When viscosity is assumed to be 0, it means that its surfaces will not be subjected to any shear stress. When its surfaces will not be subjected to any shear stress, then what type of forces will be applied on the surfaces? That will be equal to surface force, and surface force will come into picture because of the pressure. So, Euler equation write the equation of motion which relates the surface force to the acceleration with the help of force is equal to mass into acceleration, and acceleration can be written in terms of the velocity gradient, right. So, for that what we do, we select a parallelepiped in a Cartesian coordinate framework x, y, z, 3-dimensional coordinate system in a fluid regime. This is a fluid regime, and these fluid elements are having size dx, dy, dz in x, y, z direction. Now, to develop Euler equation, first we have to write the surface force, then we have to write the body force. Surface force comes into picture because of the pressure at the surfaces, and body force comes into picture because of the weight component or because of the acceleration happening in x direction, y direction, z direction for this parallelepiped. So, what is the pressure acting on this left face in x direction? In x direction it is equal to P, and with the help of the Pascal's law we can say that pressure at a point when dx, dy, dz tends to 0, then pressure at a point will be P, right. So, pressure in this direction is P, and since we are considering the element having finite size in x direction, y direction and z direction. So, what is the pressure force acting on this face in x direction? This will be equal to P plus pressure gradient del P over del x into dx. This is the pressure acting in x direction. Now, why we are taking arrow in this direction? For this one we are taking arrow in this direction, for this pressure force we are taking arrow in this direction, right. This pressure force is always applied in such a manner so that it compresses the fluid. So, by this principle we can show these arrows, right. With the help of this pressure force, if pressure force is multiplied by corresponding area, like what is the corresponding area of this face? This is dz multiplied by dy. We will get the force in x direction which is due to pressure. Similarly, we can find out the body force. So, with the help of this we can find out the surface force. Similarly, we can find out the body force, and we can write the momentum equation in x direction, y direction, z direction, which is the basis of writing the Euler's equation. So, what is the net force on this fluid element in x direction? The net force on this fluid element in x direction is equal to rho xx dx dy dz. What is xx? Xx is the body force in the x direction per unit mass. Xy is the body force in y direction per unit mass. Xz is the body force in z direction per unit mass. So, this is the force per unit mass. So, we have to multiply it by mass. What is mass? Is equal to rho density, mass per unit volume, multiplied by volume of the parallelepiped. Volume of the parallelepiped is dx dy dz, plus this is the force acting in the direction of x, P multiplied by area. This is acting in positive x direction, and minus P plus del P over del x into dx multiplied by area. This is acting in negative x direction. you refer this P base figure, this P multiplied by corresponding area is acting in positive x direction and this one is acting in negative x direction. So, what is the net force acting in x direction, right, is equal to this force minus this force. So, with the help of the figure and by defining the body force, we can write the net force acting in x direction for this parallelepiped. So, what is the net force acting on this parallelepiped in x direction is equal to rho xx minus del p over del x into dx dy dz, and dx dy dz is volume, basically volume of this parallelepiped. Similarly, we can find out the body force in y direction, which is given here, and surface force in y direction, which can be calculated with the previous figure after defining the pressure force acting on both faces in y direction. So, we can find out what is the net force acting in y direction. Similarly, we can find out what is the net force acting in z direction is equal to rho xz minus del p over del z into dx dy dz. So, after knowing the force on this parallelepiped in x direction, y direction, z direction, we can write the momentum equation. So, force is equal to, this is the force acting in x direction. We know that as per Newton's second law of motion, force is equal to rate of change of momentum in that direction, right, for control mass, right. So, for control mass, mass of this fluid element enclosed in these parallelepiped remains same, which is equal to dx dy dz multiplied by rho. This is the mass inside the parallelepiped multiplied by velocity in x direction is the momentum in x direction and d over dt. So, rate of change of momentum in x direction is equal to force in x direction. Similarly, we can write the momentum in y direction and momentum in z direction is equal to, this is the momentum, rate of change of momentum in z direction is equal to force in z direction. So, this is the equation, momentum equation in x direction, this is the momentum equation in y direction, and this one is the momentum equation in z direction, right. For simplification, we can write dx over dx dy dz, since it is same. So, it may be cancelled and this may be written as d over dt is equal to xx, where xx is the body force in x direction per unit mass minus 1 over rho density, the rho is density, del p over del x. So, in a simplified manner, the Euler's equation can be written in x direction, y direction and z direction. With the help of this equation, what is du over dt? This is the total derivative in x direction. This may be written as del u over del t. This we have studied when we talked about the total derivative or material derivative, which is summation of local acceleration plus convective acceleration, u del u over del x plus v del u over del y plus w del u over del z. So, du over dt may be written as this term, del u over del t plus u del u over del x plus v del u over del y plus w del u over del z in a Cartesian coordinate framework in x direction. What is del u over del t? This is known as a local acceleration, and what is this term? The summation of these three terms is called convective acceleration. So, basically we can write Euler's equation in the form of del U over del T plus the gradient of velocity in x direction, y direction, z direction, and here we have a body force in x direction per unit mass, and here we have a pressure gradient in x direction, right. So, it means that Euler's equation relates the velocity gradient and pressure gradient.